Dear data lovers, this is going to be my first podcast on English so far. And today with us, we are going to have Max Talanov, Dr. Max Talanov, who is the researcher at Institute of Artificial Intelligence. And the title of this podcast is going to be Do Robots Dreams of Electronic Sheep? We are going to talk about third generation of neural networks, spiking neural networks, its application, and of course, why neuroscience is so important, and maybe can we achieve artificial general intelligence and super AI or no? So, Max, thank you so much for coming and being a guest. It is all the time. It's very lovely to speak with you, to hear some good news, to learn a lot, to be honest. And that's not something that I say quite often. Okay, I'm lying about that. I'm saying that quite often to the people, but I really meant with you. I would like to start with the just questions, like as an intro. Instead of like presenting yourself, I would like maybe to explain to our listeners of the podcast, why did you choose AI in neuroscience?
Okay. Thank you for having me. And our story starts in 2014. I worked in Fujitsu, and we've been dealing with not a problem. The organization was like, possibly you heard about that, infrastructure as a service. And so there are a lot of incidents. Incidents had a textual description. And so the idea was, with AI, how can we solve that automatically? So that was the idea of, possibly one of the first systems to automate this incident solving. And at that moment, I got this idea, I got this vision, I got this problem that behavioral strategy of humans is actually determined or identified by their psycho-emotional states. For example, if you got a task, we usually have a task in limited time frame, like for 10 minutes. And when you start the task, what do you feel? And what do you do?
Okay.
Usually you concentrate and try to carry on. And if 5 minutes...
Try to solve it in smaller scale to see how I can adapt. What is the first thing? Do I have limited skill sets or not? Can I just proceed? Thinking a little bit more strategically, thinking after that doing business. Or if it's something simpler, just start doing and figure it out during the way.
Absolutely, yeah. But if 5 minutes passed and you haven't had any progress, what do you feel and what do you do?
I feel a little bit anger, and I'm going to be a little bit bothered about something. And okay, I'm very stubborn, so I'm going to try harder until I solve the problem.
Let's remember that you are going to try harder. Okay, 7 minutes passed and you haven't made any progress. What do you feel and what do you do?
I don't know. Maybe if it's 7 minutes, I'm gonna search something on the internet to see how I can do it.
Good. So you've changed your behavioral strategy from trying harder to search for the answer somewhere else. And if you failed and if you haven't found anything on the internet, for example, and 9 minutes passed and you haven't had any progress, what do you feel? What do you do?
I'm gonna... Well, to be honest, that's a good question. I would try to be completely honest, to think outside of the box by myself, to find a solution based not to try harder on my skill set I have been normally using. I will try to think a little bit broader and to see what strategy didn't I pull, to maybe rethink about the problem. Maybe I didn't understand the problem. Let's go back to the basics, understand, and start again.
That's interesting answer. That you're first one who answered this way. Usually it's like panic and ask for help, someone else. But the example
that's why I organize a conference for 4,000 people.
Yes, sure. But the example is about how we change the behavioral strategy based on our psycho-emotional state that changes just because of the time.
Yeah, that's right.
The situation is the same.
99% of people do react like you said. Basically, start panicking and start screaming, why can't I be solving? Like, okay, don't panic.
Yes. So the thing is that when you have limited resources, and we usually have it in any environment, and so because of those resources, because of the time, we have different psycho-emotional states, and these psycho-emotional states actually identify our behavioral strategy. So it's really, really important for these kind of systems, artificial intelligence systems, for example, to have these kind of emotional mechanisms. And that put me in the one interesting other question, actually rose my interesting other question. So how actually emotions work? How they change the calculations in our brain. And because I was a software engineer, I was software architect at the moment, I was interested in the calculation. So the calculation brought me directly into neuroscience, because all the calculations done in the cell level, in neurons, and we know that. And that's how I jumped into the neuroscience, computational neuroscience, that is mainly done by spiking neural networks, the topic of our talk today. And eventually in 2014, in October, I left Fujitsu and got back to academia, got back to the university, and started neuromorphic computing and neurosimulations laboratory in the university. And that's how we got yeah.
It's very interesting. It's not that often that you can hear that people from the industry come back to academy, because if I understand correctly, you felt that in the industry you couldn't progress more in the field what you're doing. And that's something, what does it mean? For the listeners, that mean that we are talking about a really deep tech, something that that will be deployed in the future, and the future is made not today but yesterday. It started.
Sure.
People don't understand that it's not something just happening by the mere point of luck. Luck is when you have a lot of and I saw the NASA pilot saying that when you're having a lot of luck with piloting the airspace flight. But the thing is, with that luck, everything's pre-calculated, and still you need to have luck for that. It's like calculated risk is totally different management. So basically, it's also like when we are talking about. When we are talking about the how to say, neuroscience as well, like neuroscience, longevity, and we can go forward. We had an episode actually with a good friend of mine from HTech, who is basically our partner, sponsor of this podcast. Is about the longevity, and basically that what we're trying to achieve is basically how cancer works actually. So we need to rethink about the problem and what the issue is. What I wanted to say, how I met you, I wanted to just share this experience with our listeners, is that first time I saw you, I didn't saw your face. I saw your leg being moved by basically third generation neural network. So basically, this was the spinal cord project, like that you use non-invasive method with just electricity, so you can utilize AI to move muscle on your basically leg, and you can basically walk with using of AI. And this is something that is basically, when I saw, I said, are you fucking kidding me? This really exists. This is solving a lot of problem, like basically globally, like, and I said, like, okay, this guy I need to meet this guy. He need to get his his spotlight at the DSC, and that spotlight turned out to be the whole breakout session for Neuro AI with 6 of top researchers right now, like globally, top researchers globally, who are doing neuroscience. One talking about fungal machines, others about mnemonic transistors, and the rest of it on some different levels. But maybe you can tell us a little bit more about Spinal Cord Project in the first place, and after that, a little bit more about that Neuro AI con and everything else.
Yes, sure. With pleasure. It started a bit later. So it's like 2015 when I met Victor Yerochin, who actually was on DSC 2023 physically. And that is really nice. And he's going to take part in 2024. He's inventor of memory stir, memory stir device. And at that moment, we've been thinking of recreation of the rat brain. So and later I met
just to explain to the people what is
memristor. Okay,
yeah, because
the memristor. So you can think of memristor as the analog of synapse in the brain. So within electronics, we have some experimental devices that has been described in 1971 by Leon Chua, and then physically discovered later in 2005, 2006 by different scientists, Strukov and Viktor Yerokhin. And that is how you can make synapses in electronics, actually.
And what is important thing to say, and this is for the engineers, for mnemonic, if I'm right, if correct, Moore's law don't apply on this device. If I understand correctly, it can be...
Yeah, because it's not transistor. It's different. So you're kind of moving out from the transistor logic, but currently we are talking about mixture of transistors and memristors, but mainly we're kind of on the edge, I think, of some pure memristor devices that could re-implement the part of the nervous system, and that could be one of the options for the spinal cord. I'll get back from the very beginning of that. So the idea was, can we recreate the part of the nervous system in electronics, for example, with memristor devices?
Okay.
And so we started working on that. First of all, we have created, with the digital computers, we created the digital model of the spinal cord with Igor Lavrov. He works in Mayo Clinic. So and that was so close to biology that we call bioplausible, that we could actually match statistically the particular animal, the particular rat. That was a rat model. And then we decided, why don't we recalculate to humans? Like that. Yeah, but that was quite complex. We optimized the system to real time, and we recalculated that, changed the parameters of neurons. And to be precise, I have to mention that we actually made what is called topology, the architecture of the spinal cord, neuron by neuron. So we copied the architecture of the spinal cord in our neural network, that is spiky neural network. That is a bit, if you think of the AI based on neural networks, it's a bit different perspective, but it's the same, well, in quotes. We'll talk about differences possibly later, artificial neural networks and spiky neural networks. But if you think it's neural network, but it kind of replicates the function by replicating the structure, by replicating the architecture of the spinal cord. And we were lucky that we were studied with spinal cord, because spinal cord is relatively small, 2,000 neurons and 500,000 connections. And at the end of the day, we managed to make it real time. And then I had this idea, why don't we test it on me? And we can, and that's what you actually saw on the video. Yeah. We got to the neurorehabilitation clinics. That wasn't done just by me. There were specialists, and they connected me, with a stimulator, and the stimulator was connected to the model of the spinal cord, so finally it worked. I mean, you actually can make the neural network that will replicate the function of the spinal cord, that will manage your muscles, and you actually will walk. Well, I'm healthy, so I'm okay. So I don't need this, but I had to relax. So that was really
what was
weird.
The feeling, basically?
Yeah, the feeling was crazy. So when we started the brain, the whole nervous system, because what you are doing, you're kind of letting your free will, or you're just giving it to the computer, if you in the physical terms, and the computer manages your leg. And your nervous system is going mad with that because what's going on? Max, give it back. Give it back. Give it back to me. So your brain hasn't sent any signal and some external, absolute external instance controlling your leg. So I had to load myself with some arithmetic because otherwise I couldn't relax my leg, and my leg was just like, all the muscles were contracted. That was really painful. But at the end of the day, I could relax. And because I loaded myself with arithmetic and some mathematics, and it goes fine. So when I could relax, so you can actually make the computer manage, or spiking neural network manage your legs, your limbs, and it works as we
and it's a non-invasive method, which is a very interesting thing, because most of the things when we saw about Neuralink, like from Elon Musk company, you need to implant in your brain, basically. You need to implant like surgery to have. This is non-invasive method, which is like totally let's say not like from engineering point of view, like having non-invasive method is totally different scale of issue than invasive method. Like when you have invasive method, you have a issue if your body is gonna accept this like foreign body. There's different biological problem, but this one engineeringly, like it can go so much thing wrong, and it's like much more complex to invent.
But here I have to say that again, we've been liking that we started with spinal cord because muscles are, well, in quotes, easily be controlled, because, well, muscles are all over the skeleton and you just stimulate that with the current and it goes through the muscle. You can see the result of that. So you can actually see the influence, the management of the model over your muscles, like directly. If you think of what Elon Musk does, they read the data from the brain. So in the level of at the level of precision that they can get from the brain, for sure, you cannot get that non-invasively. So they are doing really nice, really good job,
of course,
for the guys who have paralysis and so on, and because they have to have this precision, and that is really important for those guys. But with the limbs, you don't have to have it. It's relatively okay that you have low precision because you have to run the current through the skin first, and then only then to the muscles, right?
This is very interesting. And when we are talking about, like I said, part of our meeting each other was that neuroscience breakout session, which is going to be Neuro AI Con, the whole conference this year. So maybe you can also share a little bit more exclusively for our listeners. What is going to be this year?
Yeah, so that was really interesting and starting point. I put it like that in 2023. And that, at the end of the day, the organizers of the conference actually to make it wider and more interesting. Now we have, I guess, 9 or 10, even 10 scientists involved. That would be like really interesting scientists from different countries all around Europe. We don't have anyone from the US, but we have from China, and those guys are really, really interesting. They are making the breaking through research, including computational neuroscience, spiking neural networks, memoristic devices, already on the level of like a processor. So we can actually, currently we have the technology that is evolving that fast that we're talking about the processors made of memristors. And possibly we'll talk about that on the conference, because I've involved one guy, Alexey Mikhailov, who is going to introduce this kind of technology. And actually, we're like on a breakthrough. We're like in revolution of spiking neural networks. And possibly we're going to talk about this revolution that we are in this Neuro AI Con. And I hope that, if everything is going to be okay, Andrea Damatsky will be here physically in Belgrade. He loves really very much Belgrade, and he's making the breakthrough research on computations on fungi, on slime molds, and this crazy stuff that actually I hope, and we will see actually in the near future, would be the computation on industrial level possibly, and we could grow the computer or something like that.
Computer, that's
yes,
crazy. But basically, what I want to also say, like part of the program, like this is going to be also open call for anybody who is interested in doing biotech and neuroscience in Serbia, and not only Serbia but local countries as well. We are going to sponsor them to get like workshop, kind of like not only like people from biology but also people from software engineering and different industries, different fields of studies. They will have like workshop a day before the conference. They will have networking dinner in the afternoon with all of the speakers, and tomorrow they're going to have like free open access to the Neuro AI con as well. That's something that we are doing together. Like you're giving us brain, we're giving you the muscle. Like just don't put your brain to use on like at least electric currents or muscle. But basically, this is open call. We're going to promote that as well, and this is how we would like to also give, let's say, give our fare back to the community, and we're creating neuroscience community here in Southeastern Europe, basically. And this is, I think that it will. This is the last year was the zero step. I think this is going to be the first step, creating something very unique on this part in this part of Europe. And I think that in the next 5 or 10 years, we are going to have a lot of good things happening from this point on.
I hope it will grow and we will have a bigger, neuroscience conference, integrated with DSC, other part of the DSC.
I'm completely sure in that. So basically, this was the excellent like intro, a little bit wider, but like with neuroscience, you cannot just simply have like 1 or 2 minutes explaining something. You need to go into details.
Yes.
Or like, what is this? What is this? This is like similar to quantum mechanics as well. Like, basically, like if you're talking basically the quantum principles are basically integrated in a neural science. So basically, you cannot go one without the other. So let's talk a little bit more about spiking neural networks, or SNNs, and why they are called third generation of neural networks. What is the difference between the artificial neural networks, like all of the clusters, and why are so interested in that, especially in the field of neuroscience?
Well, to start with, if you want to compare what we have with artificial neural networks, artificial neural networks, they started in 1943, I guess, by introduction of the model of McCulloch and Pitts, and they developed in 1956 when Frank Rosenblatt provided new model, that is called perceptron. We all know that, and this model is still used in artificial neural networks. I will talk about some problems of artificial neural networks in comparison to spiking neural networks. For my position here is that spiking neural networks, we have nice example of that. It's our nervous system. Spiking neural networks that works for us every day, every second, every time we do anything. It's spiking neural networks, and it works in spikes, and we have this example, and that is really useful example. So, for example, and then we get to this point, and recently we're in process of publishing this paper. So, a comparison of energy consumption. For example, the energy consumption of artificial neural networks, and we didn't pay attention for that till recent times, till ChatGPT, to be honest, is like several orders of magnitude higher than what we see in biological spiking neural networks, or even memoristic. That's what we've been talking about, spiking neural networks. So why it is that bad? So the problem is that we didn't actually pay much attention to that. We've been just implementing some simple principles. And there are several ways that we lose energy, actually. Feed-forward approach, for example. And data sets. They are massive. But you have to process this data. And for that, you have to pay actually with the energy. You cannot process the data without the energy. And the massive data means massive energy consumption.
And basically, when you say energy consumption, like what just popped through my mind is like we're talking about like desalinization like as an issue because it's utilizing too much. It utilize too much power.
Yeah.
And I think that there is that power needed for utilization right now with the development of technology is one magnitude lower than what we are using normally for AI. And we're like, what? like okay, this is just like for me that's bullshit. Then like come on, like we are already using much more for AI. But energy consumption is very important. Important question. We are talking about also civilization development. Like people don't understand like that. Dyson spheres, objects in the. That's how you measure basically what is the advancement of civilization by how much energy they need to consume. Basically. So what is happening right now is something that we are having like a little bit of spike in our civilization. That's how you measure from physical point of view.
Yes, absolutely. We measured, we used for the biological spike in neural networks, actually brain, we used literature, data from the literature, but for artificial neural networks, we used just physical measures. For spiking neural networks on memory-assistive technology, we used physical measures. And you could say that you have, for CPUs, that is the worst case. If you have artificial neural networks running on CPUs, you have 8 orders of magnitude higher power consumption for the training and compared to the spiking neural networks implemented in memory-assistive devices or biological ones. As for GPUs that we had at that moment for the experiments, we have 6 orders of magnitude higher. Yes, and it's ineffective. It's that ineffective, unfortunately. We have comfortable ways to do the things. It's not implemented in the hardware, it's software and so on, but we have to pay for that.
Microsoft will not like this podcast for sure.
yes. But actually they pay. I mean, OpenAI, they pay. They pay for terawatts of energy to train ChatGPT. In ChatGPT 3, in ChatGPT, even worse than that, because they increase the data set. And every time you increase the data set, you got better results, but you have to pay for the training. And if you got it several orders of magnitude increase of your data sets or several times, you have to pay for that either. So it's unavoidable. And then you have this, brain, which uses not terawatts of energy, but 20 watts. Why is that so? How many neurons do we have in our brain? It's
billions of billions.
It's 100 billions, right? And synapses is 10 power 15. It's more than what we got, at least announced in ChatGPT, and we have this efficiency. So why we have this big gap between those two technologies? Because the first one is literally ineffective. So we got to this position, and then, we had... extension of the project we'll be talking about spinal cord, we got interesting effects that we got from biological neural networks, and we tested that, and that's what I call self-learning. So having the feedback loops from the muscles to the spinal cord, we can do the self-learning. It means that the spinal cord is being self-adopted to the feedbacks that it got directly from the muscles. So the information is being generated in this loop from the spinal cord to the muscle and back. And that's how you get this reduction of, that's one of the ways actually, how you get this reduction of energy consumption. So you don't need to have the massive data set because the information is being generated in feedback loops in your nervous system. And that is one of the key principles that you got in nervous system on the level of spinal cord, on the level of cortical column, which is small segment in the cortex, on the level of limbic system and cortex, on the level of the whole brain and the outer world, because we got those feedback loops all the time working.
Basically, that's how the nature works. Like it's function feedbacks, like loops. If the nature is like basically
absolutely
is going to going to create homeostasis based on what is happening right now as the current state. And this is how also like when you look like how we as humans are growing, like small baby is having like very unstructured movements, but it's learning like step by
itself,
step,
self-learning, right? So you don't have to program babies. We don't program babies because we don't need that. Our nervous system, I mean, all the humans.
Life will be much easier if you can program babies.
Yes, sure, but
of course, joking.
So this is one of the way to save the energy. So we have to get rid of feed-forward architecture. So we have to get to the feedback loops, and the whole nervous system be organized like a hierarchy of feedback loops. That's what we got.
My question to you is basically the math behind SNN and artificial neural networks. By your your expertise, what is more complex math-wise, not anything else?
Oh, so as for mathematics underneath of that, definitely SNNs are more complex than ANNs. ANNs is mainly the adder and the threshold function that what you got from Rosenblatt model. And that is really, really simple. That's why possibly it's really popular.
Yeah, that's why I asked this question, because I had I have discussion with the people that I explained from the US, like principal scientist of Snap, and I asked him about Jacobians on changing from the Descartes to the spherical coordination, because the universe has models that are much easier calculated, physically, in space. They are not to look at the Descartes. And he said, I know that, but I'm not to use that. And he has 2 PhDs actually. And what turned to get me thinking, when I was talking with them, that basically the future of AI is actually in implementing more complex mathematical principles that you need a time to verify. And that's what led me to thinking that the future of AI is not in big companies, but is going to be back to the academies, not sponsored by the big companies, which is maybe counterintuitive what is happening right now, because we need to give some time for the math to work itself out, feedback loop, principle of feedback loop, give some time to understand how it's functioning. And basically this is something that I sure is going to be the future of it. And we are talking about the future. My question to you is, what do you think will come after SNN? Because the future of SNN, where do you think, speculate, let's say?
So the future of SNN is more or less clear for me. What will be after SNN, I really don't know at the moment. So as for SNN, I can dream of SNL technologies, spiking technology, non-digital technology. And the difference, I'm going to be a bit technical, is that you don't have the discrete time. So in SNNs, in our nervous system, we don't have discrete time. Why that's so? Because we are event-based. We are really event-based because we have to react accordingly to some event, I don't know, tiger or whatever, threatening, non-threatening event. Otherwise, we're kind of delayed and could be eaten, or something bad could happen to us. To our ancestors for sure. And so we have to act, we have to build the system event-based. So that's how we get rid of this discrete time. And discrete time is one of the sources of ineffectiveness of current, actually, digital systems. And that was, again, we have the example. We have a nice example. And that is not really complex. If you think of spiking sensors, if you think of spiking feedback, embedded in spiking feedback loops with spiking systems like for robotic systems or implantable devices, or you could get it in the data centers, that could be spiking data centers. That not much of the problem at the moment. So we know more or less how to solve that. There are some problems to deal with for sure, but we more or less understand how it works in the nervous system. We have some examples. We have some technical ideas already, some technical implementation. So we're kind of halfway. If you think of artificial neural network, it's kind of in between of digital calculation and spiky neural network. So we're kind of in the middle. Yeah. We're not final with that technology. It's, well, simple, but we have much better technology as a spiking technology. Well, possibly we could think of spiking Wi-Fi sometimes, or I don't think that spiking technology will substitute digital technology. I think that it will it will be the nice addition to the digital technology. There will be digital world and the spiking world that emerges at the moment, and that is not only
this is interesting.
My words. There are actually Intel and IBM. They already have chips or spiking neural networks, and you can buy, the laboratory can buy it for $10K, for $10,000 for the research purposes. Their problem is that they don't get the understanding how they can use that. The problem is the usage. But we have nice usage again in our nervous system. The thing is that you kind of have to have this perspective shift from classical AI problems of natural language processing and computer vision processes, but possibly even in that domain you can get some advantages.
Are we talking about augmented humans, perhaps?
Sorry?
Here? Are we here talking about augmented humans?
Sure. Sure. Yeah, why not? And you get this nice integration. So your nervous system talks spikes, and you could get the electronics talking spikes. Actually, that's what we've done with memoristic spinal cord. So we created the complete electronical schematic with only 5 memoristic neurons that replicated the part of the spinal cord, and that reproduced the rehabilitation process of the rat. So we actually could match with electronics the results from the rehabilitation of the animal, of the rat, because of the self-learning capacities of the memoristic devices. So we replicated that. So we're talking about self-learning electronics, hardware, self-learning hardware that could, as our nervous system, self-adapt to the environment. That's what we are talking about. That could be really useful for the robotics, implantable devices.
Yeah, I totally agree. I totally see the use cases there. Like basically, that's something that we are talking about. Like I think that we are talking like in the future, like having like on one hand you have augmented parts of the humanity, and it says that you have like AI that's using as the let's say assistant to like humans to actually achieve our full potential. To be like, of course, there is like tons of things that we need to discuss from ethical point of view, and we can also talk about that. But basically, my like embedded synergy with our body is particularly very, very famous use case. But you have also done some paper published recently about energy consumption. So basically, and we are talking about data centers, like spiking data centers, for example. I think that can be interesting to maybe see if a national data center, which is tier 4, to maybe dedicate some, to maybe try to see if there is a room to maybe dedicate one smaller part to see how we can utilize for bio, especially because Bio4 campus is very important initiative of Serbia. I think that this can be very, very, very cool use case in the future, to be honest. Like, let's try this. Let's try this. If you're going to dedicate some resource into that, money, intellectually, let's try to build something as well, something that was not built maybe before.
Absolutely, yes.
Like, that's what the engineers and inventors and like explorers are doing. And you're one of them. Sure. And what is like just crossed my mind when we are talking about simple ANN. You know that you're talking with a real expert when somebody says artificial neural net. They are simple or like. My question for you, why I was asking the future of SNN. There is a lot we're talking about augmented humans right now. So my question is, like, I would like to do a little bit of myth busting, and you're thinking about two topics. Okay. First one is artificial general intelligence, and the second one is super AI. How do you see it, and do you think it's achievable?
To be honest, there is a problem with this term artificial intelligence and artificial general intelligence. It's not really clear what the guys mean when they say artificial general intelligence. But, well, with this term, I was introduced in 2000, I guess, 15, when in my lab, I invited P. Wang, who is one of the pioneers in that AGI field. And there is big conference, AGI, that is called AGI. I guess it's led by Ben Kurzweil. He's one of the pioneers. He created a robot that is meant to be Goetzel. Sorry, not Kurzweil, Goetzel. But the problem is, it's not really clear what you mean, actually, when you say artificial general intelligence. It has to provide some expertise in several domains, several tasks, and then you get to what are the several tasks.
I was thinking like more when people say artificial general intelligence, I think that the common, like, let's say, it's not defined. I can totally agree on that. But people think that AGI is something that can replace human. Like, let's say, completely like the artificial intelligence, which can replace human behavior, human emotions, basically.
Yeah. So let's make brain.
Yeah.
Let's make brain. And that's
right.
Yeah. So I have a simple answer. I prefer to actually be more physical rather than abstract. And that's why I'm biased, to be honest. I'm computational neuroscientist, and that's why I'm biased. I'm looking from the perspective how your calculation is done, how you calculate in neurons and so on. And you have an example like a brain, right? So from this perspective, I would like to create the brain rather than general intelligence as something abstract. If that matches your definition of AGI, okay, fine, that's fantastic. Let's do the brain, and that will be AGI. And that will, more than that, that will help a lot of people. If you think of the artificial part of the brain as a prosthesis, you could help guys with stroke, for example, and because you could substitute with your electronics, you could substitute some neurons that are injured and so on and so forth. If you have nice interface, not just electronics, but the interface, because the interface is a problem too. But you got this, at the moment unexpected, interesting side effects like neuroprosthesis or self-learning robotics and so on and so forth, creating neuron by neuron, creating the part of the nervous system or the brain, linguistic centers, visual centers, and so on and so forth. Guys with stroke, guys with Parkinson, guys with neurodegenerative disease, Alzheimer's, so on, so on, so they actually need that.
Yeah. I totally agree on that, and this is really interesting. Do you think in what time frame? Not is it, but in what time frame you think this is achievable?
I think that we're going to face self-learning. Well, let's say really simple spinal cord in 5 years.
Really?
Yeah, I think so.
This is very cool. Okay, and
we will live in a different world from that time, but I think it's realistic to say that we will have this circuitry made in hardware, and that will demonstrate integratability. Let's say, for example, with rat muscles or in a robotic system, and this approach will be used later to develop the parts of the brain, parts in plural of the brain, and possibly we could combine the brain someday. But that would definitely require from us different leap, different jump into the technology that is currently unknown, undone. So what we are talking about now, well, like cutting edge technology, let's say like thousands in plural of memory registers on the chip, like processor already. Thousands, like 4,000 up to 500,000. But before that, several years before, like 3 years before or 2 years before COVID, for example, we've been talking about like 1, 2, 3, 20 memory registers only on the chip. But now we're talking about thousands. So we got the leap already. So actually, potentially,
and we have what is important thing. We have experience of creating this leap Architecturally, we have experience with traditional computers. We understand how to create this. Of course, people don't understand from ENIAC to Macintosh, or whatever, like Windows, whatever, part of the computer. It has a lot of let's say back and forth. It wasn't just a straightforward a path. We have now experience how to create leaps in the technologies, which is going to just feedback loop. We are talking about. This is very interesting thing to say. And I think that this is something that is going to be much faster than maybe we can expect.
Sure, that's why I'm talking about 5 years. That's what I see. Other scientists, what I see, I've been talking to the scientists and the conference members since last year in November, and I think it's realistic. But we have to get this paradigm shift. We have to start looking at spiking neural networks as the example of the nervous system, with the laws of the spiking neural network that has been already implemented and tested by nature, and we have it in our bodies.
This is excellent. This is excellent thing, and I would like just to cut the question with super AI, because we have started something very because we can talk about it in the end, a little bit more about very very short. It's not going to happen but we can come to the point that. But you have said one thing which can spark very interesting philosophical debate as well. And this is basically do robot streams of electronical shift. Basically, is if you replace part of the human brain with something which is augmented, is that still us? And what will this is one thing that which raises a question. The second one, what does it make us as the whole? And the third, from the physics side, is are the electrons basically the bearers of the free will of humans or not?
So many questions. Okay, so getting back to the extension, right? So I had that experience with this neuro prosthetics controlling my leg. So as I said, first time I had really weird reaction of the nervous system. It wasn't prepared, let's say. But the thing is that the nervous system is the, let's say, mechanism that is self-adopting all the time. So at the end of the day, my nervous system adopted to the external control from the computer. Because of this self-learning capabilities of the nervous system, and you can actually extend your nervous system. You can actually, as you said, augment your nervous system with the devices, and that will become the part of you. So you kind of have an extension with that, and that. Before that moment, actually that started in 2002. Kevin Warwick made an experiment. He got the implant here in medial nerve, and this is called Utah array with 100 electrodes. So he got the surgery, and that was wire full, so with wires technology, not wireless. So he had this big bulky controller, and he could first extend his nervous system with the rangefinder, so he can actually at the bat he can actually feel the distance with his nervous system, and then he controlled the robotic hand through the Atlantic Ocean through the internet. So he got his nervous activity, neural activity from the medial nerve, and he was contracting the muscles and like that, and he could control. He was in the US, and he could control the robotic hand in the UK. So through the internet, through the Atlantic Ocean, and thirdly, he managed to integrate his nervous system with the nervous system of his wife. So they got two implants, and when she contracted her muscles, he can actually feel that. He can actually perceive, and that is human-to-human integration, an extension of us, of you, as a person to someone else. So I usually
but you still being you, basically,
You kind of you, but you have the feeling. What if you can perceive emotions of someone else, of your wife, for example, right? She having completely different levels of that, and you can actually feel You don't just see like what we do at the moment with empathy and so on. Now you can actually feel that in your brain. What does it mean to feel someone else's emotions with your brain, within your brain? That's, well, we don't know. We don't know. But that would be the
uncharted
extension.
territories. Yeah.
Yes, that would be extension of you with someone else, not just the device, but the personality. And that is completely different world. That is completely different universe.
Yeah, basically what you're saying, it has a lot of sense that, well, basically we are humans, we are shaped by experience we have. And what we do, what we learn, what we see, what we feel from that experience. And experience, something like that, will change us in terms that we will be maybe more reasonable, or maybe we will understand better wives. Maybe we will finally answer that question. How to understand female. Joking, of course. But the thing is, this is still not something that, this is something that we still have our free will to choose how we're going to deal with this. It's not something that's just going to integrate in our body. So we said, okay, if I would like to, I see that if I put my hand on the hot stove, it's going to burn me. But if I need to stop my kid for making the same mistake, I will jump and I will put my hand before him. So it's not going to stop me because I know it's going to hurt me. So basically, I still have a free conscience. And I think that with this like part, how do I see it? Basically, it's going to create two different aspects. One is to further tap into what does conscience mean for the humans. And I think that's going to be unbelievably interesting, because this is going to be the first time that we can really connect something that is science and spirituality, to be honest, like on some level, because you can calculate. This is the next step for me. But on the other hand, also, like, can we then teach robots like to be more humanized?
Oh yeah, that is a really interesting question. Last year on DC conference, actually, exactly, I was talking to Kevin Legrandieu. Kevin, sorry, your surname is too complex for me to pronounce, but I hope I'm right in pronunciation. And he was looking at, let's say, emotional, how do you put that, engine, right? That I was presenting at that conference, like basic mechanism to evolve or to create, to design the ethical robotic system, ethical robotics. And that could be the key to teach, to create and teach the robots to be ethical, to coexist with us, and possibly empathy, to have that implemented in the robotic system. But you have to have it. You have to have it in your artificial intelligence system, or if you like, brain. Otherwise, you don't. There is no mechanism to implement empathy, because you cannot feel emotions, because it's not in your brain. There is no at the moment in artificial neural networks. There is no neuromodulators, serotonin, dopamine, noradrenaline that we know, and there are more of that. It's not implemented there. It's not there, but you can do that with spiking neural networks. You can actually implement, as I said, the part of the limbic system. Well, there are some problems, but we more or less understand. Some bits are missing still, but we more or less understand what is the, let's say, biochemical mechanics underneath of that. And at least on the level of the understanding, we can do the things with that.
This is excellent thing to say, because I was speaking with Louis Sacco, who is also he's a good friend of the conference. That there's tons of research like he was involved in. He's like one of the greatest living mathematician right now. And he said that basically what research do suggest that there are two like for the normal human behavior, there is a two undistracted let's say receptors or whatever, inhibitors that they are creating our happiness. One is to achieve mastery of something without, like, for example, when playing guitar, you're doing for yourself and you're feeling very happy for it and for feeling. And the second one is teaching others passing the knowledge to others, like telling the stories, etc. These are the two biggest, like what researchers said, that the two biggest dopamines, like giving like mastery by yourself, and after they're passing. And if the human, basically you can say that people who are not having dopamines when doing that, they are like on the very end of the normal distribution of normal behavior, actually. And they are like called, like, let's say, psychopathic like behavior. Like, at least if you don't basically enjoy in like doing something to master something, or that. And this was like, when you think about it, in the end, what nature teaches us, that in the end everything is very simple. You complicate things because you will not like to accept maybe the answers that you will get.
Yes.
But basically, we are coming back to energy consumption, spinal, SNNs, basically, spiking neural networks. Maybe it is much more simpler than we think it is. Like that, maybe we just need to be a little bit more understandable that nature already did something before we even think about it.
I don't know how to answer on this question, because brain is the most complex system that we know. If we don't go like planet or universe, like this scale, and we have to, and you're definitely right that we have to understand the mechanisms and why it is like that. Is it why it is evolved like that, and why we have this? For example, emotions. Why do we have fear? Why do we have happiness or disgust or some other emotions? Basic, social, and so on. That creates the complexity. But they're there for a reason, and we know those reasons why they have evolved, why they're still there, why evolution didn't cut it and threw it away. So. And this is the key, I guess, to build the AI that we really want to build, that will at least communicate as human to human, or we don't have this feeling of plastic dialogue. So that's what we have with ChatGPT, for example. Yes. Well, the very basics of, for example, learning is spike time independent plasticity, for example. Well, it's kind of simple, but because there are several layers of the abstraction that you have to understand and keep it in mind all the time, starting from molecules to the brain, it creates the complexity of the whole system. And that's why you need, to be honest, that's a different perspective that we haven't talked about, and that is actually relevant to the conference. You have to get all the things in your brain, in your mind, and start thinking from all those levels at the same time. And then that is the complexity of AI. That is the complexity of intelligence. That is the complexity of the brain. And when you got all those bits and pieces, starting from molecule to the brain, in your mind, then you could start to understand all the effects, all the phenomena that we see in the brain and human behavior and artificial behavior, possibly.
Yeah, this is like this is very interesting. Like I think, like, and basically, thank you so much for sharing this. With this, like Max, I would like to thank you once again for being our guest. It was very interesting for me. Like you don't have a very, very often, like I said, time to speak with somebody who say and they're a little bit simpler. But also, like, I think this is something that you share with us, like your way that you think that in the next 5 to 10 years, let's say, that we are going to live in totally different world. Like, and I think,
yes, that will be different technology, right?
Yeah, and this is something that I think is very, very relevant to everyone who would like to understand not only AI and data, but as well like to understand where we are going globally and where it can lead us. So thank you so much for your time, and dear listeners, thank you for being with us, and hopefully I think this is going to be very interesting for you. I'm sure that it was interesting for me. Thank you.
Thank you very much.